Welcome to the Deep Dive. We're here to plunge into some really complex, sometimes mind-bending ideas and hopefully emerge with some clearer insights. Today, we're definitely venturing into the bizarre world of quantum mechanics. It's a place where, let's be honest, our everyday intuition just often falls apart completely, and our specific destination is one of the most enduring puzzles in physics, the violation of Bell inequalities. Now, for decades, this phenomenon, which basically shows quantum reality, defies our classical ideas of cause and effect, local realism, it's been really intimately tied to quantum entanglement, that famous spooky action at a distance. But what if that connection, that long-held belief, isn't quite as fundamental as we've always thought? Our mission today is to really dig into and unpack a genuinely audacious new paper. It's by Kai Wang and colleagues, just published July 11th, 2025. They're making a claim that it could really shake up our understanding. They're saying Bell inequality violation can happen even with photons that are not entangled. Instead, they argue, it arises from something they call quantum indistinguishability by path identity. So get ready to maybe recalibrate your reality a bit.
And that's exactly it. This is why this work is potentially so significant. It really isn't just some technical footnote. This paper offers a genuinely different perspective on the very origin of that conflict between quantum mechanics and local realism. The authors themselves say it has intriguing consequences for the foundations of quantum information science. It forces us to really reconsider some core assumptions about what makes the quantum world tick.
Okay, let's break this down then. For as long as I've been following this stuff, when people talk about Bell violations, it's always presented as the ultimate proof.
Right.
Proof that quantum correlations are just stronger, fundamentally different than anything classical physics can manage. And the key ingredient, the sort of magic sauce in all those experiments, has always been entanglement. Where multiple quantum particles, photons for instance, get linked up, sharing this coherent superposition of states. That's what allows those correlations that seem faster than light, stronger than classically possible. It's been the absolute bedrock.
Right. And what's truly, I think, revolutionary here is how this new paper deliberately moves away from entanglement as the only story, at least in their specific experiment. They're arguing that this quantum indistinguishability by path identity is actually the root cause. Think about it, like Feynman famously said, the interference of single particles, that double-slit experiment idea, has in it the heart of quantum mechanics. When you have different ways for something to happen, different paths, and they are completely, utterly indistinguishable, you cannot tell them apart, even in principle then their probability amplitudes add up, that's quantum interference. This paper is basically saying, hey, this fundamental principle applied in a clever multi-photon setup is enough to violate Bell's inequality without needing entanglement.
Okay, so if it's not entanglement creating these super strong correlations, how does this path identity thing actually do it? Can you give us a bit more intuition on how summing amplitudes in this setup gets strong enough to beat the classical limit? And maybe clarify again how this indistinguishability is really different from entanglement, because as you said, entanglement also involves interference ideas, but across multiple particles.
That's a really good question. It gets right to the core of their argument. So entanglement, yes, it creates these shared quantum states between particles, linking their fates no matter how far apart they are. That leads to strong correlations. Path identity, though, is subtly different. It's not about the particles being internally linked in some entangled state beforehand. It's about making the potential pathways from different sources so incredibly identical, so perfectly overlapped, that by the time the photons reach the detectors, you've completely lost any information about which photon came from which source along that specific path. Imagine not just identical twins, but identical twins taking identical routes through identical tunnels to arrive at the same spot. You can't tell who is who based on the path. It's the fundamental indistinguishability of their origins and trajectories leading to the measurement point. When these possibilities become indistinguishable, the quantum wave function explores all of them simultaneously. And it's the interference between these indistinguishable probability amplitudes, constructive or destructive, that creates the non-local correlations violating Bell. The outcome isn't set locally. It emerges from this global wave-like interference pattern.
Got it. And just quickly, remind us why violating Bell is such a big deal. What deep assumption about reality does it challenge?
Right. A Bell inequality tests local realism. That's two big classical ideas combined. Realism means things have definite properties, like position or polarization, even before we look. Locality means nothing, no influence, can travel faster than light. If you violate a Bell inequality, quantum mechanics is fundamentally incompatible with at least one of those assumptions. Maybe properties aren't real until measured, or maybe there's some faster than light influence, or maybe both. This paper offers a potentially new mechanism for why that conflict happens. So let's dig into their experiment, because it's pretty ingenious in how it achieves this path identity. They use 4 probabilistic 2-photon sources, let's just call them I2, 3, and 4. Each one spits out a pair, a signal photon, horizontally polarized, and an idler photon, vertically polarized. Now, the clever part is the alignment. They take, say, the signal photon path from source I and the signal path from source 3, and they align them so perfectly that they both occupy the exact same spatial mode, let's call it A1, heading towards Alice's detector. They do similar things for other paths, going to Alice, A2, and Bob, B1, B2. Because of this precise overlap, if a photon arrives via path A1, Alice has absolutely no way to know if it came from source I or source 3. The paths are indistinguishable. Alice and Bob then measure coincidences. They look for pairs of photons arriving together, A1 and A2 for Alice, B1 and B2 for Bob, and they engineer something called frustrated interference. This is really key. They can basically tune knobs interferometric phases, alpha for Alice, beta for Bob, to either encourage or suppress the generation of these 4 photon detection events. The setup ensures, as they state, that photons on the same path are indistinguishable in every degree of freedom.
Okay, so the indistinguishability is baked into the physical setup. And crucially, you mentioned they dealt with entanglement. The paper is very explicit here, isn't it? They say any initial entanglement, like in momentum or frequency from the sources, was deliberately destroyed. They use single-mode fibers and filters, essentially measuring those properties strongly. They say very clearly, therefore, we cannot utilize these internal entangled degrees of freedom in the Bell inequality test. This wasn't just a lack of entanglement. They made sure it wasn't there to isolate this path identity effect.
Exactly. That's the critical control. No entanglement allowed. So with that established, they went for the Bell test. They calculate these joint probabilities and correlation functions, E, alpha, beta, using the rates of detecting all 4 photons simultaneously. Now, detectors just click or they don't, right? A click is like a +1. There's no physical Mach 1 detector output. So they use a standard technique. It's analogous to Mathis's law and polarization optics. To get the effective makers 1 outcomes needed for the CHSH calculation, they shift the phase setting. So measuring +1 when Alice's phase is alpha plus pi, that's mathematically treated as measuring makers 1 + 1 at the original phase alpha. This relies on the correlations having a nice predictable cosine shape as you vary the phase, which they experimentally confirmed. This whole approach fits perfectly with a wave perspective. The -1 just represents measuring along an orthogonal basis, where interference is destructive for the +1 outcome. It's a standard way to build the correlation function.
Okay, meticulous setup, careful analysis, so the million-dollar question. Did they actually violate the CHSH Bell inequality? What was the result?
They certainly did. The numbers really tell the story. They measured the Bell parameter, S, to be 2.275 plus or minus step 0.057. Now remember, the classical limit, what local realism allows, is S equals 2. Anything above that is non-classical. The absolute maximum quantum mechanics allows, Thoraldson's bound, is about 2.828. So 2.275 is significantly above 2. As they put it, it violates the Bell inequality by more than 4 standard deviations. That's statistically very robust. It's a clear signal that local realism fails to explain their results.
Wow. Okay, so the interference they created, driven by path identity, cannot be accounted for by local realism. But you mentioned something else striking about the local measurements. That seems really important for their argument.
Yes, this is absolutely crucial. When they looked at Alice's detection rates by themselves, or Bob's rates by themselves, just the twofold coincidences at each station, those rates showed no interference patterns. They didn't change as Alice or Bob varied their local phase settings, alpha or beta. This is huge because it rules out the possibility that the violation is just some local artifact, something Alice could see on her own. Instead, the interference, the violation, only shows up when you correlate their results. When you look at the 4-fold coincidences, it arises from the correlation between the 2 parties. This mimics what happens with entangled states. Local results look random, but the correlations are strong and non-local. It means Alice couldn't guess Bob's phase setting just by looking at her own detector clicks. The weirdness is purely in the shared statistics.
That is fascinating. Local results are flat, but the correlation shows interference and violates Bell. But the paper goes even deeper into almost philosophical territory, doesn't it? Asking about what happens when interference is destructive. Where do the photons go?
It does, and this is where it gets really counterintuitive, perhaps pushing towards a stronger wave interpretation. When the phases alpha and beta are set so that the 4-photon coincidence rate drops to 0, or nu zero, due to destructive interference, the immediate question is, okay, the sources were on, where did the photons go? The paper, citing Bohr's idea that physics concerns what we can say about nature, suggests something quite radical. They propose, we merely create a possibility of generating 4 down-converted photons rather than actually generating those 4 photons.
So the photons aren't really generated in that case.
That seems to be the implication they're exploring. It connects deeply with a wave-centric view. They emphasize this is different from quantum eraser experiments. They say which path information never exists, and hence need not be erased. The paths are inherently indistinguishable. They then highlight the truly counterintuitive part. When the interference is fully destructive for that 4-photon outcome, they argue there's no consistent set of combinations of physical down-conversion emission processes that could lead to that outcome anyway. Therefore, they conclude it's incorrect to argue that the state ray that representing 4 generated photons is responsible for the Bell violation, since this process actually cannot happen when the interference is destructively. In essence, if the wave conditions forbid the outcome via destructive interference, the particles corresponding to that outcome simply don't come into being. The potential was there, but it wasn't realized. It's about the interference of possibilities, not just particles traveling paths.
That's pretty mind-bending. If photons aren't always generated, and Bell violation can happen without entanglement, driven by this wave-like interference of paths, what's the bigger picture here? Does this shift our fundamental view of quantum mechanics?
I think it certainly pushes us in that direction. The authors believe this work gives profound insights into the fundamental origin of the counterintuitive characteristics observed in quantum physics. It directly challenges the entanglement-centric view of Bell violations, offering this different perspective based on indistinguishability and interference hallmarks of wave phenomena. It strongly suggests that the wave-like nature of quantum possibilities might be sufficient on its own to produce these deeply non-local effects without needing the specific particle-linking mechanism of entanglement.
And what about the practical side? Quantum information science. They mentioned intriguing consequences.
Right. While the paper focuses on the foundational physics, the implications are potentially huge. If powerful quantum correlations, the kind needed for violating Bell inequalities, can arise without entanglement. Well, entanglement is famously difficult to create and maintain. It's very fragile. Could we potentially leverage this path identity mechanism for quantum technologies? Maybe quantum computing algorithms or quantum cryptography protocols that relied on interference of possibilities rather than entangled states. It could open up new avenues, perhaps leading to more robust or conceptually different quantum devices. Imagine secure communication based not on shared entanglement, but on ensuring specific paths are perfectly indistinguishable. It's speculative, but definitely intriguing.
Okay. But like many groundbreaking experiments, there are often caveats or loopholes, right? They mentioned the locality loophole.
Yes, they're upfront about that. In this specific experiment, Alice's and Bob's stations and their phase settings, alpha and beta, were not space-like separated. That means, in principle, there was enough time for a light speed signal to travel between them, leaving the locality loophole technically open. There could theoretically be some classical communication coordinating the results. They also mentioned the sampling loophole, which relates to detector inefficiencies. Maybe you only detect a biased subset of events.
So how do they address these?
They express confidence, drawing parallels with the history of entanglement-based Bell tests, which also faced these loopholes for decades. They expect that future hardware improvements, faster switching, better detectors, greater distances, will allow these loopholes to be closed just as they were for entanglement. Interestingly, some wave-based interpretations might actually view the sampling detection issue differently. If destructive interference means a photon possibility simply doesn't lead to a detection, maybe it's not a loophole or a faulty detector, but an inherent feature of the wave mechanics. A misdetection is just the wave canceling itself out at that point. But their overall conclusion is optimistic. They expect that with further refinement, quantum mechanics will finally prevail, reinforcing its validity, potentially illuminated by this new perspective.
Wow. Okay, this has been quite the journey. We started thinking entanglement was the only way to get these bizarre Bell violations, and now we see this compelling case where quantum indistinguishability, this fundamental wave-like interference of possibilities, seems to achieve the same thing. It definitely broadens the picture.
It really does. It's a fantastic reminder that quantum mechanics still holds deep mysteries, and our understanding is constantly being refined. Just when you think you have a handle on it, something like this comes along and makes you rethink the fundamentals. It's what makes the field so exciting.
Yeah, this paper really pushes us to ask, what is the fundamental source of quantum weirdness? If it's not always entanglement, maybe it's something even deeper about interference and indistinguishability, or the wave nature of reality itself. So, for you, our listener, here's something to chew on. If Bell violations can happen without entanglement, possibly explained by a more wave-centric view, does that ultimately make the quantum world feel more unified and perhaps less reliant on spooky connections? Or does the idea of interfering possibilities feel even stranger, something to keep exploring?